Hey guys, Mr. McKinney here, just doing part 2 of our videos on concavity and points of inflection. In part 1 we talked about concavity, and now we're going to be talking about points of inflection. Both of these ideas have to do with the second derivative. Alright, so the point at which a function changes concavity is called the point of inflection. And the value of the second derivative at a change in concavity is 0 or undefined. Basically, the thing to take away from this slide is that if f double prime is equal to 0, or if f double prime is undefined, that's where we're going to have a possible point of inflection. We have to make sure that the concavity actually changes, and if it does change, so if f double prime goes from positive to negative, or from negative to positive, it would either have to hit 0 or it would be undefined. And if it does change from positive to negative or negative to positive, that's what's called a point of inflection. You'll hear us refer to it as a POI. So a POI is where the second derivative changes sign, and it would hit 0 or undefined at that point of inflection. When you give a point of inflection, make sure you're giving a coordinate, an x and a y value, because it's a point, and a point has an x and a y. When you give extremes, you're only giving the y values, but for a point of inflection, you give the x and the y. This is what it would look like. So you have a function that's concave down, it's looking like a frown, and it switches to a function that is concave up, it's a cup, and the point at which it switches from being concave down to concave up is the point of inflection. Over here, I'm going from slopes that are positive to slopes that are less positive, to 0 to slopes that are negative. So the whole time the slope is decreasing. And then I'm going from slopes that are negative to slopes that are 0 to slopes that are positive. The whole time my slope is increasing. So again, concave down is where the slope is decreasing, concave up is where the slope is increasing, and where it switches would be called the point of inflection, or a POI. This is a very important summary slide that I always like to show to my students. So if you have a place in your notes where you're putting important things, I would make sure that you put this information. It's a nice way to summarize what's going on in this unit before we get to the word problems. So basically, extrema has to do with the first derivative. That's what Mr. Jansen's video covered the other day. If the first derivative is 0 or undefined, that's where you have critical points, and these are possible extrema. The extrema means that we've got a max or a min, and it's actually going to be an extrema if f prime has a sign change. So if f prime goes from positive to negative or negative to positive, then you actually have a local max or a local min, and possibly the absolute max or absolute min. That was all from Mr. Jansen's video. From my videos, we're talking about concavity, which is the second derivative. And concavity, if the second derivative is 0 or undefined, that's where you're going to have a possible POI. And it's actually a POI if the second derivative has a sign change. So if the second derivative goes from positive to negative or negative to positive, and that's what we were just talking about. I wish that we didn't have this special word called critical points, but the AP exam and Math Excel will refer to critical points. That just means that the first derivative is 0 or undefined. I just wish they called them possible extrema, because then everything would match up. You'd have possible extrema and possible POIs, and then actual extrema and actual POIs if there's a sign change. Looking for that sign change is one of the most important things you'll do when justifying your answers on the AP exam. And the way you'll organize your work is going to be with these tables that we're about to do. So fill in the tables and then sketch the graph for this given function. And what we mean by filling the tables and sketching the graph is we're going to find the first derivative, and then we're going to find the second derivative. And for each of those functions, we're going to figure out when is it equal to 0 And then we're going to check and see if there's a sign change on the first derivative and check and see if there's a sign change on the second, or on the first derivative and on the second derivative. So let's look at the first derivative. We want to know when 3x squared minus 12 is equal to 0. So 3 times x squared minus 4 is equal to 0. 3 times x minus 2 times x plus 2 equals 0. So x could be 2 or x could be negative 2. These are the critical points. They came from the first derivative. The second derivative, I'm going to say when is 6x equal to 0? That happens when x is 0. That's a possible point of inflection. So now that I know the x values, positive 2, negative 2, and 0, I'm going to make tables to check and see if there's a sign change. And when I say a sign change, I'm looking for positive going to negative or negative going to positive on the first derivative and on the second derivative. So let's organize our information a little bit. All right. So let's put it into the tables now that we've got a little bit more room. Sorry for the delay. You can fast forward. All right, here we go. So when I'm looking at the first derivative, so here's the first derivative, I wanted to know when this was equal to 0, so I had negative 2 and positive 2. The second derivative was equal to 0 when x was 0. So again, we were looking at f prime, which is the first derivative, and f double prime, which is the second derivative. Now, the first derivative was 0, f prime was 0 when x was negative 2 or positive 2. So f prime was 0. So then I want to look at, is the first derivative positive or negative? I don't actually need to figure out the value here. I just need to know if it's positive or negative. And again, this was 3 times x minus 2 times x plus 2. So if x equals, let's say, negative 10, a negative number. So that's negative, negative times negative is positive. Let's say if x is 0. So this would become a negative times a positive. That's a negative. Let's say if x was like positive 10. 10 minus 2 is 8 times 12. These are both positive. Positive times positive is a positive. Again, we're not looking for the actual numbers. We just want to know if it's positive or negative, because the only place that the first derivative can change from being positive to negative or negative to positive is when it's equal to 0 or when it's undefined. And that was at these values. So this is a potential, or not a potential, this is a local max. Over here we've got a local min. And you can plug in negative 2 into the original function and plug in positive 2 into the original function to figure out the actual value of your local max and your local min. And so if we did that either using a calculator or by hand, we'd get 11 here and negative 21. Down here on the second derivative, so again, we said 6x equal to 0. So the second derivative is 0 when x was 0. Sorry for that writing over there. So now I just need to check the second derivative on each side. So when x is less than 0, any number less than 0 times 6 is going to give me a negative value. I don't know why it's doing that. And then any number greater than 0 is going to be a positive value. So x is concave down. Sorry. Your function f of x would be concave down or concave up on either side of 0. Now, a lot of times we're going to put it all in one big table, and I think it'll make more sense in this big table. So hopefully you just fast forward through that last part. And I'll show you what I mean by the big table on the next one. This is what the sketch would look like. We found our local max and we found our local min. And then if we look back here, since it was increasing before, we would know that there's no absolute min, because before this function hits this local max, it was increasing the whole time. So we were increasing the whole time, meaning we had an arrow pointing down there, so no absolute minimum. Over on the right side, we have a positive first derivative, meaning that the original function is increasing again. And that's what we have here. So first derivative was positive, first derivative was negative, first derivative was positive. So my original function was increasing and then decreasing and then increasing again. The second derivative was negative and then positive, so we were concave down and then concave up. So concave down and then concave up. So on the AP exam, a lot of times you'll have to justify whether a function is increasing or decreasing, or whether the slope is increasing or decreasing, and then you're talking about concavity. And you're going to use these tables to help organize your information. So just find the first and second derivative and find out when they're equal to 0. All right, let's look at another example using position. So if we talk about position and we want to talk about the velocity and the acceleration, we would be looking at the first derivative and the second derivative of motion. So if our motion was f of x, then our velocity would be f prime, and our acceleration would be f double prime. And instead of f, a lot of times you'll have s of t, so then we're going to be looking at s prime, and we're going to be looking at s double prime. So let's go ahead and make our individual tables, and then we'll make a combined table. And this one gives us an interval going from 0 to 6. So let's look at the first derivative. S prime of t would be 6t squared minus 30t plus 24. And then down here we'll look at the second derivative. The second derivative would be equal to 12t minus 30. Now, if we let's start with the second derivative. If we set 12t minus 30 equal to 0, 12t equals 30, t equals 2.5. So that's the only value that I need to put into this table, because the second derivative is 0 when t is 2.5. If I put in a number less than 2.5, I'm going to get a negative. If I put in a number greater than 2.5, I'm going to get a positive value. All right, now going back to the first derivative, if I set this one equal to 0, I can factor out a 6, and I'd get t squared minus 5t plus 4 equal it to 0. I can factor out factor it, t minus 4, t minus 1. So t would either equal 4 or t would equal 1. So those are the values I'm going to look at here when I'm looking at the first derivative, because the first derivative was 0 at both of those values. And if I plug in a number less than 1, like 0 or 0.5, both of these would be negative. Negative times negative would be a positive, so I'd be increasing here. If I plug in a number in between here like 2, I'm doing a negative times a positive. That's going to be a negative number, so I'm decreasing. And then if I plug in a number bigger than 4, I'm increasing again. So if we think about this, when the velocity is positive, the position is increasing. When the velocity is negative, position is decreasing. And then over here, we're thinking about the acceleration. So when the acceleration is negative, the velocity is decreasing. And when the acceleration is positive, the velocity is increasing. All right, now let's put it all together on the same table. So again, here are derivatives and the values at which they're equal to 0. So you would have a local max, and then you'd have a local min, looking at where the first derivative changes sign, so going from positive to negative or negative to positive. You have a point of inflection where the second derivative changes sign from negative to positive. Your initial value would have been at 7, and then you're moving in the positive direction, then you're moving in the negative direction, then you're moving in the positive direction. This would be the max position, not the maximum velocity. The maximum velocity would happen when the second derivative was 0. So this would actually be the minimum velocity because we're going from negative to positive. So the maximum velocity would have been at one of the endpoints, but we're not talking about that in this video. Again, this would be the local min of position. So when the velocity is 0, that's when you're going to have either a max or a min, or a possibility for that. When the acceleration is 0, That's when you're going to have a point of inflection on the original function. All right, we're going to do one more example in the last video and then a whiteboard practice.